A bolt of lightning does not fall out of the sky. That flash you see, that blinding white streak that seems to drop from the clouds and slam into the ground, it's actually racing the other way, up. From the dirt, the rooftop, the tree, back toward the storm. And it does this so fast that your eye gets the whole thing backwards. For most of human history, everyone who ever looked up at a thunderstorm believed lightning comes down. It doesn't. In the final, brightest instant, it climbs. Here's the piece that's genuinely hard to swallow. The stroke actually travels from the ground into the cloud. But because the strike takes place so quickly, it appears to the unaided eye that the opposite is true, and this return stroke is more than 99% of a lightning bolt's luminosity. So the part that lights up the entire sky, the part you actually see, nearly all of the light you associate with lightning, is moving upward. We've been reading the most common electrical event on the planet in the wrong direction for 200 years. And it gets stranger the closer you look. Because nobody, not a single physicist alive today, can fully explain the exact spark that starts the whole thing. We'll get there. If you like the feeling of the ground shifting under something you thought was settled, subscribe and hit like. This channel lives on exactly this kind of question. The ones that look simple and turn out to be bottomless. Let's start where the lightning starts. Not with the flash, with a cloud quietly turning itself into a battery. Picture a towering thundercloud on a summer afternoon, the kind that boils upward for miles, flat-bottomed and dark, with a top that flattens into an anvil where it hits the ceiling of the lower atmosphere. Inside that cloud, there is a war going on, between hot air rushing up and cold air sinking down. And in the middle of that churning, something almost absurdly gentle is happening. Tiny ice crystals, light as dust, are riding the updraft toward the top. Falling against them, heavier and softer, are little pellets of what's called graupel, basically soft hail, slushy ice the size of a peppercorn. Nothing dramatic, just ice bumping into ice in the freezing dark. But those collisions do something remarkable. When the rising ice crystals collide with graupel, the ice crystals become positively charged and the graupel becomes negatively charged, and the updraft carries the positively charged ice crystals upward toward the top of the storm cloud. The heavier graupel, carrying the opposite charge, sinks toward the middle and bottom. And so, particle by particle, collision by collision, the storm sorts itself out. Positive charge piles up at the top. Negative charge sinks to the belly. It's like shaking a jar of salt and pepper and watching them, impossibly, separate into two neat layers all on their own. Do this a few billion times a second across a cloud the size of a mountain range, and you've built up a voltage difference so enormous it staggers the mind. The top of the cloud and the bottom of the cloud are now like the two terminals of a battery, except this battery is several miles tall and holds enough charge to light a small city. If only it could let go. Now I want to be honest with you about something, because this is where the polished school textbook version quietly falls apart. That business about ice crystals and graupel swapping charge, we know it happens. We can even reproduce it in the lab. Researchers have built wind tunnels that fire ice crystals at a spinning target to watch the charge jump. And what they found is unsettling in its complexity. The dominant effect on charge transfer turned out to be the relative humidity at which the ice crystals grow. It exceeds the impact of temperature and liquid water content, with higher humidity always promoting stronger negative charging. Tweak the humidity, and the charge can flip sign entirely. Change the temperature by a few degrees, and everything reverses. So we can describe it, we can chart it, but if you ask the deep question, Why exactly does one bit of ice steal electrons from another bit of ice when they touch? The answer gets embarrassingly thin. Cloud electrification is one of the oldest unresolved puzzles in the atmosphere. The most familiar, most photographed force of nature on Earth, and its very first step, how the cloud charges up at all, is still argued over in journals. I find that beautiful, honestly. We mapped the outer planets before we fully explained a raindrop rubbing against a snowflake. But let's say the battery is charged. The top of the cloud glows with positive charge. The bottom sags heavy with negative. Now what? Now the storm has to discharge. And this is where lightning does the thing your eyes will never catch. It does not leap all at once. It gropes. From the belly of the cloud, an invisible finger of charge begins to reach down toward the ground. But it doesn't move in a smooth line, the way you'd draw it. It jumps. A short segment, maybe 50 yards, then a pause of a few millionths of a second, then another jump, forking, branching, feeling around in the dark like a blind hand looking for a doorknob. Scientists call this the stepped leader. In the most common type of cloud-to-ground lightning, a channel of negative charge, called a stepped leader, will zigzag downward in roughly 50-yard segments in a forked pattern, invisible to the human eye, shooting toward the ground in less time than it takes to blink. You have never seen a stepped leader. Nobody has, not with the naked eye. It carves out a branching path through the air, the path the visible bolt will later use. But on its own, it produces almost no light. Think of it as someone secretly laying a fuse across the entire sky, one dark segment at a time, and you don't even know it's there. And while that invisible fuse is creeping down, the ground is not just sitting there waiting to be hit. The ground reaches back. This is the part almost nobody knows. As that finger of negative charge descends, the ground below it and everything sticking up from the ground starts to feel the pull. The charge in a rooftop, a fence post, a flagpole, a blade of grass, even the top of a person's head gets tugged toward the sky. And from these points, faint tendrils of opposite charge begin to rise up to meet the descending leader. As it nears the ground, the negatively charged stepped leader causes streamer channels of positive charge to reach upward, normally from taller objects in the area, such as a tree, house, or telephone pole. These upward reaches are called streamers, little glowing threads climbing off the tips of ordinary things, straining toward the storm. For a fraction of a second, the sky and the earth are both reaching for each other across a shrinking gap. It's almost tender, if it weren't so violent. And then they touch. The instant a downward groping branch of the leader connects with an upward straining streamer, the circuit closes, and everything the storm has been storing, that city's worth of charge, is suddenly free to move. When the oppositely charged leader and streamer connect, a powerful electrical current begins flowing, and this return stroke of bright luminosity races back up toward the cloud at close to a third of the speed of light. That's the flash. That's the bolt. And it is moving up. The blinding channel of light you see rips from the point of contact on the ground and races back up the pre-built path toward the cloud at that phenomenal speed. Because the path is already set, the return stroke does not need to waste time ionizing new air, allowing it to move with such velocity. The fuse was laid downward, in the dark. The fire runs upward, in blinding light. The whole sequence, invisible leader down, streamer up, connection, return stroke back to the cloud, happens so fast it's genuinely difficult to describe in a way that feels real. The actual time between the appearance of the stepped leader in the cloud until the return stroke is about 1/133rd of a second. You blink slower than that. You could not clap your hands fast enough to match even the pause between one step of the leader and the next. And that flicker you sometimes see, where a bolt seems to strobe or pulse a few times, that's not your imagination, and it's not one strike. Once the path is open and glowing, the storm can dump charge down it again and again. Additional discharges occur typically at intervals of 50 to 100 milliseconds and are usually preceded by a dart leader that travels, without stepping or branching, down the existing main channel. Same road, reused. A negative cloud-to-ground flash consists of one or perhaps as many as 20 return strokes. 20 separate strikes, all up the same channel, all in less time than it takes you to say the word lightning. Your eye smears them into a single flickering line. So we've got the whole machine now. The cloud builds the battery. The leader gropes down. The ground reaches up. They kiss. The light roars back to the sky. Clean. Explained. Textbook. Except for one detail that ruins everything. Go back to the very first move, the leader stepping out of the cloud. To start that, you need a spark. You need the air itself to break down and turn from an insulator into a conductor, because air, normally, refuses to carry electricity. That's the whole reason you can safely stand in a room full of it while it's saturated with radio waves and static. Air holds its ground. To force air to break down and let a current through, you need an electric field of a very specific, very large strength. Physicists have measured that number precisely. They've also measured the electric fields inside real thunderstorms, sending balloons straight up into the belly of the beast to read the voltage. And the numbers don't match. They don't even come close. Thundercloud electric field observations have consistently yielded peak values that are an order of magnitude weaker than the dielectric strength of air. Read that again. The field inside a storm, the very field that's supposed to rip the air open and fire the leader, is about 10 times too weak to do it. By the known laws of physics, the lightning you watched last summer should not have happened. The spark should never have caught. The storm has the charge, sure, but it does not, on paper, have anywhere near the punch needed to pull its own trigger. This isn't a rounding error. This isn't a measurement someone will fix next Tuesday. This is a genuine gaping hole at the center of one of the most studied phenomena on Earth. We can film lightning at 100,000 frames a second. We can track it, map it, count its strokes. And we cannot say for certain what lights the match. So what does? What actually pulls the trigger when the storm's own field is too feeble? The leading suspect comes from the last place you'd think to look. Not from the storm, from outer space. The idea goes like this. Constantly, silently, the Earth is being bombarded by cosmic rays, particles hurled at us from exploding stars and unknown engines across the galaxy, some of them carrying almost unimaginable energy. When one of these ultra-high energy particles slams into the top of the atmosphere, it shatters into a cascade, a downpour of high-speed electrons raining through the air. Now, drop one of those blazingly fast electrons into a thundercloud's electric field, a field that's too weak to start a normal spark, but not nothing. Something surprising happens. Runaway breakdown occurs when the drag force that electrons experience moving through air is less than the electric force acting upon them. In such cases, the electrons will run away, gaining very large amounts of energy. That's the key word. Runaway. A single electron, already moving near light speed, doesn't get slowed by the air the way a slow one would. Instead, the storm's field grabs it and accelerates it further. As the runaway electrons collide with air molecules, they generate other runaway electrons, plus X-rays and gamma rays, resulting in an avalanche of high-energy particles. 1 becomes 2, 2 becomes 4, 4 becomes a torrent, an avalanche of relativistic electrons tearing a conductive path through the cloud. And that path, that ionized channel carved by particles from a dying star, may be exactly what the storm needs to finally let go.
The physicist who first worked this out in the early 90s proposed something that sounds like science fiction and is taken completely seriously. That a bolt of lightning striking your backyard might be triggered, in part, by a particle that began its journey in a supernova tens of thousands of years ago on the far side of the galaxy. There is mounting evidence that this form of discharge is the reason why the electric field in thunderclouds is limited. In the absence of cosmic rays, the field could reach values an order of magnitude greater than those observed in clouds. I want to be careful here, because this is science, not a magic trick, and scientists themselves are careful about it. The runaway idea is compelling, but it is not settled. Neither the conventional nor the runaway mechanisms are completely satisfactory. Neither can explain all the observations. The honest state of the field is that we have 2 incomplete answers and no complete one.
Of course, we don't know what actually initiates lightning, but recent observations have demonstrated that these discharges could be the trigger. Sit with that for a second. Every thunderstorm you have ever driven through, every flash that lit up your bedroom window as a child, every bolt in every summer of your entire life began with a spark that, by our best physics, is not supposed to be able to start. And the best guess we have for what does start it involves the corpses of exploded stars raining invisibly through your ceiling right now. The trigger of lightning is, to this day, an open problem, which raises an obvious and slightly uncomfortable question. If we've been wrong about which way lightning moves, and we still can't explain what lights it, how confident should we really be about anything we think we know about storms? The answer, it turns out, is not very. Because to understand how far we had to come, you have to go back to a man flying a kite in a storm, and to another man 1,000 miles away who tried to copy him and did not survive the afternoon. He was the first person in history killed by the thing we're about to describe, and the way he died has never been fully explained either. The date was August 1752. The place, St. Petersburg. Inside a modest laboratory, a physicist named Georg Rickmann stood beside an apparatus he had built with his own hands, a tall iron rod running up through the roof of the building, connected by a wire to instruments on his table, designed to draw the electricity of an approaching storm down into a device that could measure it. He called it his electrical gnomon. He had been chasing the same lightning that Benjamin Franklin was chasing across the ocean. And Rickmann was good, meticulous, obsessive, one of the finest experimental minds in the Russian Academy of Sciences. A storm was rolling in. Thunder rumbled beyond the windows. Rickmann had brought an engraver with him, a man named Sokolov, so that any spark he coaxed from the sky could be sketched for publication. Both men leaned in over the apparatus, watching the wire, waiting for the storm to give them something. What happened next was witnessed, but never truly understood. According to Sokolov, a pale blue ball of fire, about the size of a fist, leapt from the rod straight at Richmond's forehead. There was a bang like a small cannon. Richmond fell backward without a sound. Sokolov was thrown to the floor, stunned, his clothes scorched. When help arrived, the physicist was dead. There was a red mark on his forehead, one shoe was blown open, and part of the door frame had been split. The most careful scientific mind in the city, killed in an instant by the very thing he was trying to measure. And here is what haunts the story. What actually struck him A direct bolt? A charge that traveled down his own instrument? Or that strange blue ball of fire the engraver swore he saw? Something that didn't behave like ordinary lightning at all. The accounts couldn't agree. The physics of the day couldn't explain it. Richmond had become the first person in recorded history to die conducting electrical research, and the exact mechanism of his death slipped away with him, unresolved. We'll come back to that blue fire. It refuses to stay buried. Franklin, on the other side of the world, had done something a little smarter, though the schoolbook version of his famous kite is almost pure fiction. He did not stand in the rain holding a string that lightning struck. Nobody who does that survives. His actual proposal, the one he sketched years earlier, was the sentry box experiment. A person sheltered in a small hut, drawing charge from an insulated iron rod to prove the clouds carried electricity without becoming part of the circuit. The kite, when he finally flew it, was flown into a storm cloud that had not yet produced a strike to draw off the gentle ambient charge, not a full bolt. He noticed the loose fibers of the string standing on end, brought his knuckle near a key tied to it, and drew a spark. Small, controlled, alive. He understood, correctly, that a direct hit would kill him. Richmond did not get that lucky. The difference between the celebrated genius and the forgotten martyr was, in part, a matter of how much of the sky they let into the room. For a long time after that, people believed we more or less understood lightning. It went down, it was electricity, it was dangerous. Case closed. And for 2 full centuries, that confidence blinded science to the fact that the sky above a thunderstorm was hiding an entire secret world. One that ordinary people kept reporting and that experts kept dismissing. Because pilots saw things up there. They had been seeing them for decades. Imagine flying at night, high above a distant thunderhead, the storm below you flickering with the familiar white pulses of lightning. And then, above the cloud, not below, above, where there is nothing but thin air on the edge of space, a flash of color leaps upward. Red, sometimes bluish, gone in a fraction of a second, faint, enormous, impossibly high. You blink. Was that real? Air crews reported these fleeting flashes for the better part of a century. Colored bursts, streaks of light shooting up out of the tops of storms toward the heavens. They wrote them in flight logs. They told each other about them over coffee. And when they mentioned them to scientists, they got the same reception every time. Picture the scene, because it played out again and again in some version. A veteran pilot, hundreds of storms behind him. A man whose entire career depends on reading the sky accurately, describing to a meteorologist what he saw above the clouds. And the meteorologist, politely, tells him it isn't possible. There's nothing up there to glow. No fuel, no mechanism, no charge. It must have been an afterimage of the lightning below, a trick of a tired eye, reflection off the cockpit glass. Nothing dramatic happens at that altitude. The air is cold, stable, and holds no charge worth speaking of. What you saw, sir, cannot exist. And the pilot, who knows what he saw, learns to stop mentioning it. That's the quiet tragedy in all of this. How many people held a real piece of the natural world in their memory and were taught to distrust it because the theory of the day had no room for it. The ceiling above the weather was supposed to be quiet. Nobody believed a thing could burn up there. Everyone agreed. Everyone was wrong. There was even a warning shot from the theory side, ignored for 60 years. Back in 1925, a Scottish physicist had worked out that under the right conditions, electrical discharges should be able to fire upward from the tops of thunderstorms into the thin air above. A clean prediction. It sat in the literature, quietly correct, and nobody chased it. Predictions without pictures don't survive in science. It would take a machine and a mistake to change that. The mistake came on the night of July 6, 1989. Researchers at the University of Minnesota were testing a low-light television camera, the kind sensitive enough to catch faint flashes, for a completely unrelated project. They planned to use it to observe a rocket launch. To calibrate it, to check that it worked in the dark, they aimed it out toward the night sky over Minnesota, roughly in the direction of a distant thunderstorm far off near the horizon. It was housekeeping. Setup. Nobody expected the storm itself to matter. The camera was pointed, in effect, at the wrong part of the sky, above the storm, not at it. Later, going back through the recorded footage frame by frame, they found something on 2 of the frames that stopped them cold. Above the distant thunderstorm, reaching up from the cloud tops toward space, were 2 tall, glowing columns of light. Bright, structured, enormous. Nothing anyone had a name for. Not lightning, as anyone knew it. This thing was firing upward, high above the storm, in the part of the atmosphere that everyone had promised was empty and dark. That was it. That was the moment. Not a grand expedition, not a decades-long hunt. A camera left pointing at the horizon during a calibration test, and 2 accidental frames. That is how a phenomenon that pilots had reported for 100 years, and that a theorist had predicted 60 years before, finally forced its way through the back door into official science. The upper atmosphere flashes were real. The airmen had been right the whole time. And once scientists knew where and how to look, once they aimed cameras above storms on purpose, they discovered they hadn't found one strange thing. They'd found a whole bestiary, an entire zoo of luminous creatures living in the sky between the weather and space, each one weirder than the last. There are the sprites, and the name fits, because they behave like something alive. A sprite blooms above a powerful storm in a flash lasting only thousandths of a second, and it is vast, reaching tens of miles high, hanging in the air like a great red jellyfish, a glowing crimson dome at the top, with long tendrils trailing downward like the arms of some deep-sea animal drifting 50 miles above the ground. They flicker into existence and vanish before you could ever say you saw them. And here's the eerie part. The light is cold. This is not the roaring, white-hot channel of a lightning bolt. Sprites are cold plasma, closer in temperature to the glow of a fluorescent tube than to a fire. A faint, ghostly discharge in air so thin it's almost the vacuum of space. A jellyfish of cold red light, taller than a mountain range, breathing once and dying, over and over, above every great storm on Earth. Then there are the blue jets, which behave differently. Narrow cones of blue light that shoot up out of the very top of the storm cloud like a spout of luminous water, climbing miles into the stratosphere before fading. Where sprites bloom high and cold, jets erupt low and fast, straight from the anvil of the cloud. And highest of all, the ones with the wonderful, absurd name, elves. An elf is a vast, expanding ring of light, hundreds of miles across, flashing out flat like a ripple on a pond, up at the very edge of space where the atmosphere thins into nothing. It lasts less than 1,000th of a second. It is the faint glow of the upper atmosphere itself being briefly excited by the electromagnetic pulse of an especially violent bolt below. A halo the size of a country, blinking once, invisible to everyone beneath it. Think about what that means. There is an entire electrical realm sitting directly above the weather. A layer of the atmosphere that textbooks called quiet and dead, and it is anything but. Every night, above the big storms, red jellyfish rise, and blue fountains spout, and rings of light, hundreds of miles wide, flash across the roof of the sky. It has been happening for as long as there have been storms and skies. For all of human history, it was going on over our heads, and we simply weren't looking up far enough. And when a few people did, we told them to be quiet. But even the sprites and jets weren't the strangest thing the storms were hiding. Because it turned out, thunderstorms weren't just making light. They were making radiation. The kind of radiation nobody expected to find anywhere near the surface of the Earth. In the early 1990s, a NASA satellite called the Compton Gamma Ray Observatory was doing its job, staring out into deep space, hunting for gamma rays, the most energetic form of light in the universe. Gamma rays come from cataclysms, exploding stars, matter falling into black holes, the most violent engines in the cosmos. This satellite was built to look outward, at the far and terrible things. And it kept catching flashes of gamma rays coming from the wrong direction. Not from deep space, from below, from Earth, from the direction of the planet's own atmosphere. At first it made no sense. Gamma rays from a thunderstorm? That's like pointing a telescope at a distant galaxy and having it detect the fires of a supernova coming from your own backyard barbecue. These bursts, now called terrestrial gamma-ray flashes, were coming out of ordinary storms. The same storms dropping rain on farms and cities. Brief, intense bursts of the highest energy radiation known to physics, produced not by a black hole, but by weather. And it goes further into the impossible. Some of these flashes are energetic enough to produce antimatter. The storm briefly manufactures the positive twin of the electron, the exotic mirror stuff that physicists usually have to build billion-dollar machines to create in tiny amounts. Ordinary thunderstorms, the kind you complain about ruining a picnic, are occasionally firing bursts of antimatter and cosmic-grade radiation up toward the satellites we sent to study black holes. That should feel absurd. It should stop you. The same runaway electrons we met earlier, the ones accelerated to near light speed inside the storm, possibly seeded by particles from dying stars, when they slam into the air, they can throw off these gamma rays and briefly conjure antimatter. The storm above your house is, for microseconds at a time, a particle accelerator. A tiny, natural, uninvited cousin of the largest machines humanity has ever built. So look at what we've done to our neat little picture of lightning. We started with a bolt that goes down. It goes up. We said the storm's field lights the spark. It's too weak, and dead stars may be pulling the trigger. We said the sky above storms was empty. It's full of red jellyfish and rings of light the size of nations. We said gamma rays and antimatter belong to black holes. They're being made in the clouds over Kansas. Every time we looked closer, the storm got stranger. And I've saved the strangest for what's coming. Because there is one thing lightning can apparently do that we have never explained, never reliably reproduced in a laboratory, and never even agreed is entirely real. It doesn't strike and vanish. It lingers. It floats. It drifts through closed windows and rolls down aircraft aisles and hovers over the ground, glowing, silent, patient. And then it's gone. The blue ball of fire that killed Georg Rickman in that St. Petersburg laboratory may not have been a metaphor at all. For decades, ball lightning had one enormous problem as a scientific subject. Almost nobody serious would admit it existed. The reports went back centuries. A glowing sphere, usually about the size of a grapefruit, sometimes a beach ball,
drifting slowly through the air during or after a thunderstorm. It floated. It hissed or made no sound at all.
It could pass through a closed window without breaking it, roll down the aisle of an aircraft, hang in the corner of a room, and then either fade quietly or vanish with a bang and a smell of sulfur. Sailors described it clinging to the masts of ships. Homeowners swore it came down the chimney and rolled across the kitchen floor. For hundreds of years, ordinary people kept describing this thing in almost identical terms, across every continent, in languages that had never touched. And physicists, for the most part, looked away. It broke too many rules. A ball of energy that persists for many seconds, sometimes a full minute, should not hold together. Whatever heat or charge you put into a glowing sphere of gas should dissipate almost instantly, like a smoke ring coming apart. It should not float gently against gravity. It should not pass through glass. There was no equation for it, no reliable way to make one, and no photograph anyone fully trusted. So the safest career move was to treat every eyewitness the way those meteorologists once treated the pilots, politely, and as though they were mistaken. But the eyewitnesses had one name on their side that was hard to laugh at. Because when historians went back through the old accounts, one of the most detailed early descriptions of a glowing ball of fire leaping from an electrical apparatus during a storm came from that laboratory in St. Petersburg, the death of Georg Rickman. A ball of fire, the size of a fist, pale blue, that struck a serious scientist dead in front of a witness. A phenomenon that killed one of science's own founders is not so easy to laugh out of the room. Rickman's death sat in the record like a stone in a shoe. Whatever that blue sphere was, it had been real enough to kill. So historians and physicists started doing the patient, unglamorous work, pulling together centuries of accounts, thousands of them, and asking whether the pattern was too consistent to be imagination. And the pattern held. Size, color, duration, behavior, the way it favored storms, the way it sometimes entered buildings. The descriptions from a 17th century English parish and a 20th century Siberian farmhouse lined up far too well to be coincidence. People weren't inventing the same hallucination independently for 400 years. Something was out there. We just couldn't catch it. And then, on a night in northwestern China, we finally did. By accident, of course, the way all of this seems to happen. The place was the grasslands of the Qinghai Plateau, and a group of researchers from Lanzhou had set up their instruments to study ordinary lightning. They had cameras and, crucially, spectrographs, instruments that split light into its component colors, the way a prism does, so you can read what a glowing thing is actually made of. They were pointed at a thunderstorm, recording strikes. Routine work. Nobody was hunting the ghost. Then a bolt hit the ground, and where it struck, a glowing sphere bloomed into existence and went drifting across the field of view. It floated horizontally for a distance, changing color, glowing for well over a second before it faded. And their instruments, pointed by pure luck in exactly the right direction, caught the whole thing. For the first time in the history of science, someone had recorded the spectrum of natural ball lightning. We finally got to ask the glowing ghost what it was made of. The answer was strangely humble, and it pointed toward one of the leading ideas. Threaded through the glow were the fingerprints of elements from the soil, the very dirt the lightning had struck. This fit a theory that had been floating around for years, that when a bolt slams into the ground, it can vaporize minerals in the soil and fling up a little cloud of pure silicon, which then slowly burns in the air as it recombines with oxygen. A floating ember of vaporized earth, glowing as it oxidizes. A ball of burning ground, lifted into the air by the strike that made it. It's a beautiful idea, and it might be right. But, and this is the honest part, it does not account for everything. The ones that pass through solid glass without a mark stay unexplained. So do the ones reported far from any ground strike, or the ones seen inside sealed aircraft. There are rival theories, a whole crowd of them, trapped microwaves, tangled magnetic fields holding a knot of plasma together, even more exotic ideas, and none of them accounts for every observation. Ball lightning remains, to this day, a phenomenon that science cannot fully explain and cannot reliably create, not for lack of trying. And this is where you have to picture the labs. Somewhere, right now, there are physicists who have spent large parts of their careers trying to make a ball of lightning on a bench. They discharge enormous banks of capacitors across salt water, across silicon wafers, through carefully arranged electrodes, chasing that one specific thing, a glowing sphere that will hold together and float for even a second or two on its own. Some of them get glowing blobs that last a fraction of a second. Some get bright, drifting clumps of plasma that die almost as soon as they're born. Picture a graduate student who has spent 500 hours in a darkened lab, triggering the same discharge over and over, watching a high-speed camera, waiting for the flicker that lasts just long enough to matter, and going home, night after night, with almost nothing. The thing that a farmer sees drifting through his barn by accident, the best-funded laboratories on Earth struggle to summon on demand. Nature does it casually. We can barely do it at all. That's the quiet humiliation at the heart of this whole story. The most common electrical phenomenon on the planet still hands us mysteries we cannot solve with all our instruments. And if you want the scale of how little we understand, you have to stop looking down at the ground and let the view lift off the Earth entirely. Because lightning is not ours. Turn the cameras outward, into the solar system, and the storms are waiting on almost every world with an atmosphere. On Jupiter, spacecraft have watched lightning flash in the cloud tops, and not gentle flashes, but bolts believed to dwarf anything Earth has ever produced, ripping through clouds not of water alone, but laced with ammonia, in a storm system where a single spinning tempest is larger than our entire planet. On Saturn, one storm raged and flashed with lightning for the better part of a year, a single electrical tantrum that lasted longer than a human pregnancy. Venus, wrapped in acid clouds, may crackle with its own strange discharges. And on Mars, in the swirling dust of its great storms, there are hints that the grains themselves rub together and build up charge, the way that ice does in an earthly thundercloud. The same slow sorting of positive from negative, playing out in red dust instead of white snow. Think about what that means. The exact process we still can't fully explain here. Ice bumping ice, charge separating, a spark too weak to start somehow starting, is running on other worlds, in other chemistries, under other suns. Lightning is not an earthly quirk. It appears to be something atmospheres simply do, a language that clouds speak wherever clouds exist. And when we finally reach a planet around another star and want to know if it's alive, one of the first things we may listen for is the crackle of its storms. Because on Earth, some scientists argue, lightning wasn't just decoration. The energy of primordial bolts, tearing through the young atmosphere, may have helped forge the first building blocks of life out of dead chemistry. The same force that killed Georg Rickman may be the same force that, 4 billion years ago, helped start the long chain of accidents that ended in us. So here is where we've arrived. A bolt that climbs instead of falls. A spark too weak to exist, perhaps lit by the ashes of dead stars. A whole hidden kingdom of red jellyfish and rings of light living above the storms. Ignored for a century because it embarrassed the theories. Gamma rays and antimatter pouring out of ordinary rain clouds. A glowing sphere that drifts through walls and kills physicists and cannot be caged in any laboratory on Earth. And the same fire flashing on Jupiter, on Saturn, in the red dust of Mars, maybe on worlds we will never name. We built a civilization that can weigh a distant galaxy and photograph a black hole. And we still cannot tell you with certainty what lights the lightning that strikes our own backyards, or what that ball of pale blue fire really was. That gap between how much we can measure and how little we truly understand is not a failure. It's the most exciting thing I know. Every one of these mysteries is a door someone your age might walk through and open. If that feeling grabs you the way it grabs me, the sense that the ordinary sky is still crawling with secrets, then subscribe and stay with this channel, because we are going to keep opening these doors together, one impossible thing at a time. The next time a storm rolls over you, and the sky goes white for an instant, and the thunder arrives a few seconds behind, remember that you are not really watching something you understand. You're watching a bolt travel upward that you'll swear went down. You're standing under a battery built by colliding snowflakes, triggered by something from deep space, capped by a hidden layer of cold fire, leaking radiation once thought to belong only to the death of stars. The most familiar sight in the world, and it is still, at its heart, a message we can't fully read. The sky over your head is not empty, and it is not simple, and it is not finished revealing itself. It is full of questions, and the strangest part of all is that we still don't even know how to ask most of them.